In the last episode, we separated a vector from its coordinate description. Now we can ask a deeper question. What is a matrix? The most useful geometric answer is not. A matrix is a rectangle of numbers. A matrix is a rule that takes every input vector and sends it to an output vector. In other words, a matrix transforms the entire space. The numbers in the matrix are a compact way to record that space-moving rule. A linear transformation is special because it preserves the structure of linear combination. If we add two vectors first and then transform, we get the same result as transforming each vector and then adding. If we scale a vector first and then transform, we get the same result as transforming first and then scaling. Geometrically, this means the origin stays fixed, straight lines remain straight, and evenly spaced grid lines remain evenly spaced. Lengths, angles, and areas can change. A square can become a parallelogram. But a linear transformation does not bend a straight line into a curve. Here is the key simplification. To understand a linear transformation on the whole plane, we only need to know where it sends the basis vectors. In the standard plane, the first basis vector points 1 unit to the right, and the second points 1 unit upward. After the transformation, those two basis arrows land somewhere else. The first column of the matrix is the new location of the first basis vector. The second column is the new location of the second basis vector. Once those destinations are known, the entire grid follows. Now matrix vector multiplication becomes visible. Suppose the input vector has coordinates x1 and x2 in the standard basis. Before the transformation, that means, take x1 copies of the first basis direction and x2 copies of the second basis direction. After the transformation, the basis directions have changed into the columns of the matrix. So x is x1 times the first column plus x2 times the second column. Matrix multiplication is not magic. It is the same coordinate recipe, rebuilt using transformed directions. Common matrices are common space actions. A scaling matrix stretches or shrinks the space along selected directions. If the horizontal scale is larger than the vertical scale, a circle becomes an ellipse. A rotation matrix turns every vector around the origin by the same angle. The grid turns with the arrows, and distances are preserved when the transformation is a pure rotation. Both actions are linear because they move every point according to one consistent rule. A shear pushes the grid sideways while keeping one family of lines fixed. Squares become slanted parallelograms, but the grid is still made of straight, evenly spaced lines. A reflection flips the space across a line or a plane. A vector on the mirror line stays where it is, while other vectors move to the opposite side. These examples are useful because they show how flexible linear transformations are. They can distort shapes strongly, but they still preserve the algebra of vector addition and scaling. Matrix multiplication is composition of transformations. When you see A backs, the vector x is first transformed by B, then the result is transformed by A. So the product AB is a single matrix that represents two space actions in sequence. This also explains why matrix multiplication usually does not commute. Rotate then shear can produce a different final grid from shear then rotate. The symbols are ordered because the geometry is ordered. Some transformations can be undone. If a matrix stretches, rotates, shears, or reflects without collapsing dimensions, every output vector has exactly one input vector. That matrix is invertible. Its inverse performs the reverse space action. But if the transformation flattens the plane into a line or collapses space into a lower dimensional set, information is lost. Many different inputs can land on the same output, so there is no unique way to go back. That is the geometric meaning of a singular matrix. This view also changes how we read a linear system. In the equation Ax equals b, the matrix A is the transformation, X is the unknown input, and B is the target output. Solving the system means asking, which input vector lands on this target after the transformation? If A is invertible, every target has one input. If it collapses space, some targets are unreachable, and other targets may have infinitely many inputs. So a system of equations is also a reachability question in the output space. Here is the core picture to keep. A matrix is best understood as a transformation of space. Its columns tell us where the basis vectors go. Multiplying a matrix by a vector means recombining those transformed basis directions. Matrix multiplication means doing one transformation after another. Invertibility asks whether the space action can be undone, or whether some dimension has been collapsed. And solving Ax equals b asks which input reaches a chosen output target. In the next episode, we will attach a number to this geometric story, the determinant, which measures how area and volume scale.